Download this code from codegive.com, link in the description below. Writing efficient and fair multi-threaded programs requires understanding threading concepts, synchronization mechanisms, and ensuring that your program maintains fairness among threads. Below is a tutorial that walks you through the fundamental principles, considerations, and a code example for creating multi-threaded programs in Python. Understanding multi-threading. 1. Threads. A thread is a lightweight sub-process that can run concurrently with other threads within the same process. Threads share the same memory space, which can lead to efficiency but also introduces challenges regarding data consistency. 2. Concurrency versus parallelism. Concurrency means that multiple threads are making progress, while parallelism means that multiple threads are executing at the same time. Python's global interpreter lock, GIL, affects how threads run, particularly for CPU-bound tasks. 3. Synchronization, to prevent race conditions, where multiple threads read and write shared data simultaneously, synchronization mechanisms like locks, semaphores, and condition variables are used. 4. Fairness, ensuring that all threads get a fair share of CPU time and resources can be critical, especially in long-running applications. Key concepts. Locks, used to prevent multiple threads from accessing a shared resource simultaneously. Condition variables, used for signaling between threads. Semaphores, used for controlling access to a shared resource with a fixed number of instances. Thread pools, a collection of threads that can be reused for executing multiple tasks. Writing efficient and fair multi-threaded programs. 1. Identify shared resources, determine which data or resources will be shared among threads. 2. Use locks wisely, use locks to protect shared data, but avoid locking for extended periods. This can lead to contention and reduced performance. 3. Minimize context switching, keep threads doing meaningful work to reduce overhead from context switching. 4. Use thread pools, instead of creating and destroying threads frequently, use a thread pool to manage a fixed number of threads. 5. Ensure fairness, implement mechanisms to ensure that all threads get a chance to execute. For example, using condition variables to signal waiting threads. Example code. Here's a simple example of a multi-threaded program in Python that demonstrates these principles. We will create a producer-consumer scenario using threading, locks, and queues. Python. Import threading. Import time. Import random. From queue import queue. Shared resource, queue. Buffer underscore size equals 5. Buffer equals queue, max size equals buffer underscore size. Lock for synchronizing access to the shared resource. Lock equals threading.lock. Def producer. While true. Item equals random.randint, 1, 100. Buffer.put, item, block if the buffer is full. With lock, acquire lock to print. Print, f produced, item, buffer size, buffer.size. Time.sleep, random.uniform, 0.1, 0.5, simulate variable production time. Def consumer. While true. Item equals buffer.get, block if the buffer is empty. With lock, acquire lock to print. Print, f consumed, item, buffer size, buffer.size. Buffer.task underscore done. Time.sleep, random.uniform, 0.1, 0.5, simulate variable consumption time. Creating threads. Producer underscore thread equals threading.thread, target equals producer. Consumer underscore thread equals threading.thread, target equals consumer. Start threads. producer_thread.start. consumer_thread.start. Join threads to the main thread to wait for their completion. producer_thread.join. consumer_thread.join. Explanation of the code. 1 queue, we use a queue from the queue module, which is thread safe and manages the buffer for our producer-consumer model. 2 locks, we use a lock to avoid race conditions when printing the output to the console. This ensures that the printed statements do not get interleaved. 3 producer and consumer functions, these functions simulate production and consumption of items. The producer generates random integers and adds them to the buffer while the consumer takes them out. 4 thread creation, 2 threads are created, one for the producer and one for the consumer. Both threads run indefinitely, simulating an ongoing process. 5 thread joining, we call join, on both threads to wait for their completion, although in this example, they'll run indefinitely. Conclusion. By following these principles and using the provided example as a reference, you can write efficient and fair multi-threaded programs. Always remember to balance performance with the need for synchronization and fairness among the threads. As you get more comfortable with threading, you can explore more advanced topics like thread pools, futures, and asynchronous programming.